Welcome to this explainer. Today we are taking a really breathtaking macro to micro cosmic journey. We're going to dive deep into one of the absolute most fascinating objects in the night sky, Caldwell 91, which is affectionately known as the Wishing Well Cluster. We'll be using this incredible celestial object as a sort of lens to understand not just the universe around us, but how humanity actually navigates it, and ultimately how stars meet their end. So, grab your imaginary telescopes, because we are heading deep into the cosmos.
You know, this cluster has literally been dropping jaws for centuries. Just listen to this observation from a legendary astronomer John Herschel, all the way back in 1847. He called it the most brilliant object of the kind I have ever seen. When you have a guy whose entire family legacy revolves around staring at the night sky, calling something the most brilliant object, you know for a fact you're dealing with something truly special. Through a telescope lens, it's this stunningly rich field of stars that basically looks like a handful of glittering silver coins shimmering at the bottom of a wishing well.
But before we get too deep, let's talk about scale. 1,321. That's the distance in light years between us and the Wishing Well cluster. Think about that for a second. When you look up at Caldwell 91, the light hitting your eye has been traveling through the void for over a millennium. But here's the wild part. In the grand scheme of our Milky Way galaxy, 1,321 light-years actually makes it a relatively close neighbor. And it's exactly this proximity, combined with its crazy density of stars, that makes it so incredibly useful for modern astronomy.
If you want to find it yourself, you'd have to look deep within the Carina constellation down in the southern sky. It was officially discovered by the French astronomer Abbé Nicolas Louis de Lacaille back in 1752. Also known to astronomers as NGC 3532, it just sits right there in the galactic plane, an absolute jewel of the southern hemisphere. But as we're about to see, this cluster is a whole lot more than just a pretty face in the cosmos. So what is its practical purpose? Well, it all starts with calibrating our cosmic eyes. Because before we can study the deepest secrets of the universe, our instruments need to be perfectly tuned. Think about it like when you buy a new camera. You take a picture of a test chart to make sure everything's in focus, right? Well, for a multi-billion-dollar space telescope, a dense, rich star field with precisely mapped coordinates is the ultimate celestial eye chart. On May 20, 1990, a portion of this very cluster served as the first light target for the Hubble Space Telescope. That was literally Hubble's very first glimpse of the universe. And then decades later in 2013, the New Horizons spacecraft, the one that famously flew by Pluto, used this exact same cluster to calibrate its LORRI camera. So this single cluster of stars has successfully guided and sharpened the vision of humanity's greatest cosmic explorers.
Beyond just calibration, though, Caldwell 91 serves as a giant stellar laboratory.
You see, Caldwell 91 is an open cluster. That means its stellar populations are coeval, a fancy way of saying they are the exact same age, and they share a common chemical composition. All these thousands of stars were born together out of the exact same giant cloud of gas and dust. In science, you always want a controlled experiment where you isolate your variables, right? Well, an open cluster is nature's perfectly controlled experiment. The only major difference between the stars in this cluster is the mass they started with.
And that is exactly why researchers focus so heavily on it. When mapping the spatial distribution of targets for the Southern Open Cluster Study, or SOCS, Caldwell 91 is a premium focus. By systematically comparing this specific cluster against 23 others with different ages and chemical makeups scattered across the southern sky, astronomers can actually piece together the evolutionary history of the entire Milky Way disk. It's like a giant puzzle, and this cluster is a crucial corner piece.
But hold on, let's back up. I just confidently said we know these stars are the same age, which begs a really fascinating question. How do we actually know the exact age of a star cluster? If they are over 1,300 light-years away from us, how can we possibly measure time on that kind of cosmic scale?
Astronomers solve this using something called a color magnitude diagram. This is literally how they tell time and space. They plot the brightness of the stars on the vertical axis and the color, which tells us the temperature, on the horizontal axis. That dark, dense, diagonal band of dots you see, that's the main sequence, where stars live out their normal, stable lives just happily burning hydrogen. But look toward the top left, right where that line suddenly bends and drops off. That's called the turn-off point. Because more massive, brighter stars burn through their fuel way faster, they peel away from this main sequence first. By calculating exactly where that turn-off point is, astronomers have clocked Caldwell 91 at roughly 300 million years old.
And knowing that age brings us to a much darker phase of the cluster, the white dwarf graveyard.
Now, 300 million years might sound pretty young for a universe that is 13.8 billion years old,
But it's more than enough time for this cluster to develop to very different extremes. On one hand, you have a rich population of lively red giants. These are your late-stage, aging stars that have swollen up and are actively fusing heavier elements. But hiding right there among them is a darker reality. The cluster is known in astronomy circles as a white dwarf graveyard. White dwarfs are the incredibly dense, dead, glowing embers left behind after a star is completely collapsed. And Caldwell 91? It's absolutely littered with them.
But there is one dead star in this cosmic graveyard that stands out above all the rest. Allow me to introduce you to the heavyweight champion of Caldwell 91, WVPHAS J1103-5837. Okay, I know, the name is a total mouthful, but what this specific white dwarf represents is an absolute blockbuster discovery for astrophysicists.
The extreme stats of J1103 completely set it apart. Most white dwarfs have cores made of carbon and oxygen, and they weigh in at just a fraction of our sun's mass. But J1103 is a beast. It boasts a super-rare oxygen neon core. It has a mass of roughly 1.13 solar masses, meaning it somehow packs more mass than our entire sun into a sphere about the size of the Earth. In fact, according to the source research, this is quite possibly the most massive white dwarf currently known in any open cluster anywhere in the sky. To leave a corpse this heavy, the original star that died to leave this dense core behind must have been unbelievably massive.
And finding a heavyweight like that unlocks some massive secrets of stellar evolution. Finding such an extreme, heavyweight dead star in a cluster where we already know the exact age helps solve one of the trickiest puzzles in astrophysics. The solution lies in this chart, the initial to final mass relation. By plotting the initial mass of a star when it was born against the final mass of the dead white dwarf it leaves behind, we start to see a clear pattern. We know that small stars leave small white dwarfs, right? And we know that supermassive stars, say 10 or 12 times our sun, explode violently in supernovas. But what exactly happens to the heavyweight intermediate stars right in the middle? Do they explode? Do they collapse? By finding our heavyweight champion J1103 right there at the extreme upper limit, scientists finally have hard proof tying these heavy original stars to massive, ultra-dense oxygen neon white dwarfs. It literally anchors the maximum size a star can reach before it inevitably explodes.
So what does this all mean for us? We've traveled 1,321 light-years to look at a cluster that helped focus the Hubble telescope, a cluster that acts as a natural laboratory, and one that hides a graveyard of record-breaking dead stars. But as we peer into the wishing well, we are really just looking into a mirror. Our sun isn't heavy enough to leave behind an oxygen neon core, but one day, billions of years from now, it too will become a white dwarf. By studying the life and death of stars in Caldwell 91, we aren't just doing abstract math, we are getting a direct, sneak preview of the ultimate fate of our very own solar system. And honestly, I think that is a beautifully profound reason to keep looking up.